Additive manufacturing, since it's a very new process, the process structure property relation is even more interesting, and we even do not know many of the hidden aspects of process structure properties even after performing research for more than a decade worldwide. So in this lecture, my plan is to talk about how computational method can help us getting more insight into the process structure property relation in metal additive manufacturing process. So first, I will briefly talk about what are the uniqueness and opportunities that metal additive manufacturing provided us, and why we need computational tool to understand process structure property relationship. And then I am going to give you 8 examples of the application of computational tools in understanding process structure property relationship, particularly modeling and machine learning applications. And then I will finish with future perspective according to me, and what will be the broader long lasting impact in this field. Okay, so I was talking to Dr. Samanto right before this talk to understand the course material, and I know that Dr. Samanto has already covered the basics of additive manufacturing process. So I'm going to give you a few context. So the left hand side picture happened in 2014, so more than 10 years ago now. They needed a range in the International Space Station. But that time, NASA did not have any plan for supplying mission. And what they did, they sent a STL file from Houston, Texas to International Space Station. And in the International Space Station, they had a 3D printer which printed this fully functional range. So maybe 30 years ago, 20, 30 years ago, it would have been a science fiction, but because of additive manufacturing, we can do these things in today's world. The right hand side picture, if you see that printed metallic parts are now all over the places in all different type of industries with a wide variety of applications. So then you might ask, what is the problem? What is the main problem that we need to solve? Currently, if you know a little bit of material science, you will know that there are more than 5,000 commercial metallic alloys. And how many of them you can print, you can probably count with your 2 hands. That few. And what is the problem? The problem is we can't control successfully the structure, microstructure, mechanical properties and defects that affect the mechanical properties. So let me give you a brief context of what do I mean by microstructure. If you have taken a material science class, you know that the grain structure control the property, and the grain structure, the grain morphology look very different depending on the material, depending on the processing condition. So I took 2 very elementary examples, columnar grains and equiax grains. Now just think of this part, the top image. If you pull this part during the tensile test along the vertical direction and along the horizontal direction, you will get completely different property. And to make things worse, these long columnar grains would tend to separate from each other and the part will fail before you can expect. That situation will be completely different if we have small equiax grain providing so many grain boundaries and make the parts stronger. You can't believe that we get in metal additive manufacturing both type of grain structure, and that significantly control the mechanical properties. The other aspect of property is the phase formation. Like for example, if you compare in the same part, in the x-axis you can see this is distance from the top of the deposit. So this is near the substrate, this is near the top of the part. You see in the same part you see different type of microstructure or phase formation that completely change the elementary mechanical properties like hardness. And the third aspect of it is defect. You may have a void because of improper manufacturing process, And if you have a void like that hidden inside the part, the mechanical property will be very bad. Surface roughness, we all know that mechanical properties like fatigue is significantly affected by surface properties like surface roughness. So in additive manufacturing parts, all of these things affect simultaneously that will govern the final performance of the additively manufactured part. So why we need computational tools to solve all these problems? Um, I am just giving you one brief context. Let's say you are talking about powder bed fusion, laser powder bed fusion additive manufacturing, which is one of the very common additive manufacturing processes. What are the important variables that you can control during the experiment? Power, speed, beam radius, layer thickness, a whole lot of things. And depending on which material you need to select, there are a wide variety of material properties. So I list a few of them. There are 12 variables that can change during the experiment. Now, even if you take a two-factor design of experiment, that means you need to understand the effect of 12 variables here. You need at least 4096 experiments. Now, Dr. Samanto can tell that from the experimental point of view, doing one successful experiment sometime may take a day. So if you need to do 4096 experiments, a PhD student cannot finish his or her thesis in 10 years. So that's the challenge we have currently in additive manufacturing. And if you take just two variables, laser power and scanning speed, depending on which process you are selecting, they vary significantly for same material. Please see these are plotted in the logarithmic scale. So we are talking about not only a huge amount of experiments to understand the effect of processing condition and material properties on the final microstructure and property of the part, but also we need to cover a huge process window. So what is the alternative? The alternative is, because of the advancement of computational techniques, we can use the computational tool that can reduce the parameter space to be explored. We can significantly minimize trial and error experiment so that within a less amount of time we know what works and what does not work. Then we do experiment only for those reduced parameter window and make parts with improved quality. So that's the main mantra behind my talk. How we can use the computational tool to understand what works and what does not work. So when I say computational tool, I mean two things: modeling and machine learning. So modeling means you have a multi-physics model, you give all the input variables that I showed you in the last slide and the material properties, and it will tell you somehow the microstructure, the mechanical properties and the common defects based on scientific principles. Using these tools, we can guide the experiment by selecting appropriate process conditions. Now here I am saying a little different from what I have already told in the first slide, that this is a new process and we do not have all fundamental understanding of metal additive manufacturing so far. So you can ask, okay, then how do you make a mechanistic modeling if you do not understand all the physics? That's true. So to avoid that route, where we do not have the physics known, we take advantage of a vast amount of experimental data and use those trained machine learning algorithms that do not need phenomenological or mechanistic understanding. And we have two benefits. One is we can predict microstructure properties and susceptibility to defect formation with less amount of data without the need for fundamental understanding. And the second most important benefit, we know the hierarchical importance of variables, like which variable is more important than the other, so that when you go and do the experiment, you control the most important variables and you save a lot of time and energy and money in order to do so. So what I'm going to do in this talk in subsequent slides, I am going to provide a few examples on the application of both of these computational tools. But before I do so, I want to briefly talk about what are the different types of models that people use these days and what are the computational challenges in order to implementing them. The most elementary thing is reduced order analytical models. If you open welding handbook, so many of the scientific things are similar between welding and additive. So if you go back and open welding handbook published by American Welding Society, you will see there are analytical formula to calculate temperature, field, cooling rate, etc. Those fundamental things that people have been using for last 40-50 years. So some of those things we can borrow from the welding literature and apply in additive manufacturing process. Like for example, laser DED process. We have been doing that too, and you see you can get a very nice prediction of the temperature field, of the deposit geometry that are almost matching with the experimental observation. So that are fast, that are reduced order analytical model. You do not need to have access to a complex computational code. You can run in your laptop using MATLAB, Python, etc. Same thing you can do for laser powder bed fusion, and you see that depending on which material you are using, I have kept here 4 very common materials that we use in metal additive manufacturing. You can see that these reduced order analytical model, although they are very straightforward and simple, can identify the differences between different materials. So these are the most primitive models that one can use. Now to increase the complexity, multiphysics molten pool level numerical model. Now you know that during additive manufacturing process, you melt the material and then you deposit that molten material. You continue to do so layer by layer to make or to print a part in 3D. So the question would be, what happens inside that molten region? How the liquid metal flows driven by so many factors? What are the effects of that fluid flow in the context of microstructure and eventually defect formation and mechanical properties? If you look closely, these black vectors are showing the flow of liquid metal inside the molten region, and you will understand that there are differences in surface tension, differences in buoyancy. All these complex physics are dominating in this. And if you want to do this type of modeling, that means then you need a complex numerical methodology that will take longer time in any computer you can think of than the reduced order model that we just talked about. Now this is for only one track. If you want to do things for a real life part, like let's say for powder bed fusion, this is the top view of a powder bed, and the laser moves in specific scanning pattern. Like here I show a bidirectional pattern, zigzag pattern. How the temperature field evolves during time. Why this is important? Because depending on this spatio-temporal variation of the temperature field, you can get an understanding of microstructure formation, how the residual stress will form, how the part will distort. All these complex understanding are dependent on the temperature field. And if you want to do a whole scale, part scale model, you need to do a complex, time consuming numerical model. Similar thing is true for laser DED. You are making a rectangular block with many layers and many tracks. So sometimes these codes takes multiple days to run in order to get a complete picture of what's happening during the manufacturing process. So this is a brief overview of what are the different type of multiphysics models that we have today that we use in a regular basis for additive manufacturing. So in a nutshell, what can model do? We have been talking about the inputs, all the 12 variables that we have seen. We feed them in the model, and model spits out a wide variety of things like temperature fields, cooling rate. Temperature fields we just have seen, and you can take that and calculate solidification morphology. Like you remember I was talking about whether this is columnar, whether this is equiaxed. These are called solidification morphology. And then grain structure in 3 dimension, because depending on that the mechanical property will be varied significantly. Residual stresses and distortion for large scale parts, and then defects like crack formation, lack of fusion, etc. And I am going to give you a few examples on this. The other aspect is machine learning. So when we do not know the physics, we take advantage of machine learning. Now to me, there are 2 types of problems in machine learning that are also very relevant in the context of metal additive manufacturing. One is regression problem, where you can represent the output in terms of a continuous variable. So for additive manufacturing, let's say geometry, whether the pool is wide, how much width of the pool is, how much depth of the pool is, all these things you can represent by continuous number. Grain size, and again a continuous number. Residual stress, distortion, all these things you can represent by a continuous number. They are regression problem. In contrast, classification problem is binary or multiple classes, like for example whether defect is formed or there is no defect. Solidification morphology is equiaxed or columnar. So this is a classification problem. Now depending on what type of problem you are dealing with, there are different type of machine learning algorithms, and we are going to see the application of some of these in subsequent slides. So before I start giving my examples, can you make sure I am still audible and you can see my screen still?
Yes, we can see everything.
Okay, great, thank you. So my first example is modeling of collaborative robot or cobot assisted manufacturing. So this picture is at Iowa State in our lab. So collaborative robot is a new technique. So there was a concern that with the use of robotic technologies and automation, there might be a significant cut in jobs. So people have started thinking of how you can use or how you can combine the robotic technologies or automation technologies and at the same time take the advantage of human. So collaborative robot means it can take advantage of both the robots and the human intervention. So we have a cobot, we use the cobot for doing welding and wear art additive manufacturing, as you can see in the right hand side picture. So collaborative robot gives you a wide variety of advantages, like for example enhanced safety for human interaction, improving user friendliness and wide variety of things. The most important thing that it does not need a very detailed path programming. So if you are thinking of the traditional robot, they need a very precise G-code and M-code path programming. So a cobot does not need that. You just teach a path by a few key coordinates. That significantly improves the productivity. So we were interested in understanding that how selecting few key coordinates can change or can impact final outcome like the temperature fields, residual stress and distortion during wear arc additive manufacturing. So we investigated very simple examples, like what if you deposit a hexagonal shape. You see that depending on the selection of the teaching points, which are the 6 vertices, you can see different type of temperature field and distortion field and residual stress field. The second example is modeling of adjustable mode beam laser. So this is a work that is just published. So this adjustable mode beam laser is a new technology in the field. So we all know of Gaussian beam, Gaussian laser, and we probably have heard of a ring beam, ring type laser, or some people call it a donut beam laser. Let's say you are making this part using laser powder bed fusion. Now where you need to print tiny features like this, you need a very focused, concentrated beam like a Gaussian beam. But then the productivity will be very slow. So when you are making something like this infill, where you do not need tiny features, you can change the beam to a ring beam and you can enhance the productivity. That means you have to have a provision to switch between a Gaussian beam and a ring beam to be able to enhance the productivity when you additively manufacture a complex part like this. So what's the technology? The technology is called adjustable mode beam or AMB laser, where you switch between the Gaussian beam and the ring beam or take advantage of both the beams simultaneously. So how it works? If you see the animation, there's a core beam and then there's a ring beam, and their relative power percentages changes during the process, and people can control it using NC technologies to be able to print this type of part with improved microstructure and with higher productivity. So we are setting up a similar process here, but we have published quite a bit of modeling result on this. Like for example, if you see, if you vary the power percentage in the core beam versus in the ring beam, this picture is 100% power is assigned to the ring beam, the outer ring beam, and here 100% beam, 100% power is in the Gaussian core beam, 0% in the ring. And you will see that depending on the power percentage, you can precisely tune in the overall power density. And that means you have a complete control over the pool dimensions like pool width and pool depth. And what are the effect of that? You see, this is pure Gaussian and this is AMB with 80% power in the ring beam. You will see that the molten pool or the fusion zone, both experimentally and numerically, are quite different. And when you have this type of significant difference without changing the power, without changing the material, without changing the scanning speed, you have a complete control over the molten pool and fusion zone geometry and the temperature field. So when we understand the science behind this, we can leverage this to be able to control the microstructure. How? You see, we all know that the formation of columnar and equiax, going back to my earlier slides, and you will see that formation of columnar and equiax grains depend on two factors: temperature gradient and solidification growth rate. Both these parameters you can calculate from temperature field that we have already seen in the previous slide. Now when we do that for the core beam only, Gaussian beam only, versus an adjustable mode beam, you will see they lie in the different region. For the core beam, it's in the mixed region, some columnar, some equiax, if you can notice here from this EBHD diagram, versus if you have AMB, this is in the fully equiax region. Here you see that grains are long columnar grains disappeared. These are all smaller grains. So based on doing a very simple calculations, you should be able to predict microstructure that are also consistent with the experimental investigation. Now, understanding the grain morphology from temperature gradient and solidification growth rate, that is well established in the textbook. If you see welding metallurgy textbook, a famous textbook from a professor whose name is Sindoku from University of Wisconsin-Madison, he has demonstrated this for welding. We are taking the same principle, and for the very new technology, this is even newer than laser powder bed fusion with adjustable mode beam laser. We can prove that same thing, same fundamental science is very well applicable for new process in order to predicting the microstructure. So to make things complex, my third example is how to control the grain structure that we have just predicted. Once again, going back to basics, there are two variables. If I go back, temperature gradient and solidification growth rate. So what do I mean by that? For metallic materials, for alloys, we all know that they just do not instantaneously solidify from liquid to solid. There is a two-phase region, solid and liquid. That is true for all engineering alloys. Now what happens in that region? So left hand side you have pure solid, and this solidification front is moving at as the metal is solidifying. Now the speed at which the solidification front is moving is called growth rate. That was the x-axis variable in the previous slide. And in this region, two-phase region, if you plot the temperature variation with distance, you will see that equilibrium liquidus line that you can get from a binary phase diagram, if you are talking about a binary material, that deviates from the actual liquidus line, and that region is called the supercooling that drives the solidification process. So I am not going to very much detail into phase transformation or solidification phase transformation, but this is the understanding in a nutshell. And this temperature difference is called temperature gradient, which one was the y-axis variable in the previous slide. So these are the two variables. What Shindoku told us, this is the book I was talking about. This is the most recent edition, 2021 edition. Temperature gradient and solidification growth rate. So exactly the same plot I was showing in the previous slide. So if I go back, you will see that depending on the slope of temperature gradient and solidification growth, higher slope means columnar, lower slope means equiax. Now you see higher slope is columnar, lower slope is equiax. Depending on this value of G and R, temperature gradient and growth rate, you can identify what will be the solidification morphology. Now since we know those, we can take advantage of that and predict very precisely the solidification morphology even during the processing of same material, where earth deposition of an aluminum alloy, 6000 series aluminum alloy. Now experimentally you can see in the same deposit, at the center you have equiax grain, but near the edge you have columnar grains. How does it happen? What we did, we calculated the G by R, the slope of the temperature gradient versus solidification growth rate plot, and we know for this material 6000 series aluminum alloy, the critical G by R slope is 9 Kelvin second per millimeter square, beyond which it forms columnar grain. So across the width we plotted this G by R, and we will see that this 9 Kelvin second per millimeter square, this line, based on which this region is columnar and this region where the slope is less than 9 is equiaxed, and that is exactly following the experimental observation. And when we eventually did the grain growth simulation, we also saw the similar behavior. So even if you do not want to do a complex grain growth simulation like the left hand side picture, just by doing temperature gradient and solidification growth rate calculation, you should be able to get a very detailed understanding of the solidification morphology, and that's where scientific understanding is important. So once you know the solidification morphology, whether this is columnar or equiaxed, you can go and dig deep into it. So when I teach this subject in my class, I tell students that columnar dendrites look like Christmas tree. They really are. So if you do not know how the columnar dendrites look like, they look like this. The distance between two consecutive primary arms is called primary dendritic arm spacing. These are the primary arms, and for each primary arm, just like the Christmas tree, there are secondary arms, and the distance between two consecutive secondary arms is called secondary dendritic arm spacing. Now this secondary dendritic arm spacing is very important for determining the mechanical property, because this is the smallest dimension, smallest microstructural dimension that will provide the resistance when the dislocation moves. That means it affects the mechanical property. How does it affect? If you know the cooling rate, you can calculate the secondary dendritic arm spacing, this distance. There are formula from Matt Fleming's solidification book. Matt Fleming is a legendary name from MIT who has done all the earlier works in understanding the solidification principle and correlating the solidification cooling rate and etc. with the microstructural feature like secondary dendritic arm spacing for a wide variety of materials. So 50 and 0.4, they are constants, particularly true for one material, and here we are talking about stainless steel 316L. So you see what we did for a wide variety of laser power, we calculated the temperature field from which we calculated the cooling rate, plug them in this formula and get secondary dendritic arm spacing. And then we check in the experiment under ACM micrography, and you can see that this one, that our calculation is telling the secondary dendritic arm spacing is larger, and under ACM you can see that is indeed true. So once again, this is a proof of how you can do very simple calculation to be able to get an understanding of microstructure. Okay, so fourth example, moving forward from microstructure to mechanical property. So I want to start with an elementary mechanical property, which is hardness. Now, if we talk about hardness of ferritic steel, we know that hardness of ferritic steel are often affected by martensite formation. Like for example, if you consider grade 91 ferritic steel, which is widely used for nuclear energy applications. This is a ferritic martensitic steel. This is a CCT diagram. If you do not know what is a CCT diagram tells us, depending on how you are cooling the part, what would be the phases. Like here, if you see, A stands for austenite, and here F stands for ferrite, and C stands for cementite. So if you take a iron carbon phase diagram, you will identify these phases on a iron carbon binary phase diagram. Now M is martensite. You may know that if you cool steel very rapidly, you will end up forming martensite. Now martensite forms depending on cooling rate, but for this material you see the critical cooling rate above which it forms martensite is very low. It's 0.05 Kelvin per second. Above that cooling rate, it always forms martensite. And if you want to process this material using additive manufacturing, we are talking about cooling rate of 1000, 10,000, 100,000 Kelvin per second. So no matter how you process, you will always form martensite for this material. Okay, that part we understand. Now what happens in additive manufacturing? Things become more complex. In additive manufacturing, as you know, we deposit material in layer by layer. That means if you are depositing upper layers, you are reheating and recooling the layers that you have already deposited. What happens? That repeated heating and cooling during multi-layer deposition heats up the martensite and again cools down the martensite. That means it's a in situ heat treatment of martensite, and that is a very well-known phenomena. If you study material science, some of those martensite will become tempered martensite, and in this material the tempered martensite is nothing but vanadium and chromium carbides. Okay, so how does that affect the mechanical property? To understand that, we developed a framework that took advantage of both mechanistic modeling and machine learning. So we collected tempering data from the literature, trained a neural network. Why? So that we can get isothermal tempering data for different temperature and different time for that particular material. At the same time, we use that tempering data to be able to get the Johnson-Mehel-Abrahami equation constant. So if you do not know Johnson-Mehel-Abrahami equation, this is an equation that will tell you with time how much phases will transform from phase A to phase B. So this is a rate of phase transformation equation. So at the same time, we did the heat and fluid flow calculation, mechanistic modeling of additive manufacturing, so that we know the temperature variation with time, and then we integrate the JMA equation over the thermal cycle to be able to get the final hardness of the part. So this work we published a few years ago, but this is an example of how you can take advantage of existing database, machine learning, material science, mechanistic model to be able to find out how the mechanical property can change during additive manufacturing process. And results are stunning. You see, if we plot the hardness with respect to the distance from the substrate, that means 0 is just above the substrate, and you are going up. You see that the hardness is increasing, and after some time the hardness does not change appreciably. This is true in experiment, this is true in the calculation. Why that's happening? If I talk about lower layers like layer 1, you will see this is the thermal cycle. So what is this AC1 temperature for this material? This is 1123 Kelvin. That means if the temperature goes above that temperature, all the martensite that it formed will become austenite again. It needs to form martensite once more. Here if you see that after first cycle, all the martensite that formed, after second cycle they become austenite again. And after third cycle, same thing happened. After fourth cycle, same thing happened. But after fifth cycle, you see the martensite is not transforming back to austenite again. And because of this repeated heating and cooling, all the martensite that we formed after the fourth cycle will become tempered martensite. Tempered martensite are softer than martensite. That's why the hardness, you can see this is lower than here because of the number of thermal cycles. But that thing will be significantly different if you look near the top. 8th layer. After 8th layer, there are 2 more layers remaining, and you will see both layers, the peak temperature is going above the AC1 temperature. That means all the martensite that you formed transforming back to austenite. So there is no change in hardness. So it can tell you that if you understand how the temperature is changing, you can conclude very nicely on the variation in microstructure as well as mechanical properties. Okay, so after microstructure and property, now the remaining examples are mostly focusing on the defects, because defects apart from the microstructure largely control the mechanical properties and performance. For example, porosity. If you have pore inside the part, if you do tensile test, the part will fail before you expect. So we need to understand porosity. To me, there are 3 types of porosities in additive manufacturing, and we can visually distinguish among those 3 types of defects. First is lack of fusion. What is the origin? The origin is improper fusional bonding among tracks. In additive manufacturing, we deposit multiple tracks to be able to make a part in 3D. If 2 consecutive layers or 2 consecutive tracks do not fuse properly, they will end up having lack of fusion. And lack of fusion, that defect can vary significantly in terms of their shapes and size. Second is keyhole pore. What is keyhole? Sometimes during additive manufacturing or during welding, the temperature can go beyond the boiling point of the material that you are using. So we end up creating a vapor cavity during the process. You remember I was talking about the molten region. Just imagine in that molten region, some part became vapor, okay, a vapor region. Now that vapor region is called keyhole, because if you see the literature, sometimes that vapor region is very deep and narrow and look like a keyhole. That's why we call it keyhole. Now that very narrow and deep vapor column may be unstable. They collapse and then they create gas bubbles. If those gas bubbles cannot come out of the molten pool, they create keyhole pores. Keyhole pores are large and often rounded but of various sizes. And the third type of porosity is gas porosity, which is quite small than any of these, rounded, often spherical or elliptical in shape. Why they occur? They occur because the molten pool can pick up gases from the atmosphere. Now, I understand that we have sealing gas, but still most of the molten metals are very highly susceptible to pick up diatomic gases, hydrogen, oxygen and nitrogen from the atmosphere. If you are doing powder-based additive manufacturing, most of the commercial powders are made by gas atomization. That means you use high-power gas jet to atomize the powders. Now, during that process, some of the gases can be entrapped using the powder you are starting with. Those gases come out during the process and create gas pores. So now we know these are the three types of porosities. I am going to talk about lack of fusion and gas pore, because keyhole porosity can only happen if you perform the additive manufacturing in keyhole regime. So I am not going to talk about this. I am focusing on first and third type. Lack of fusion, the first type of defect. So you see there are pictures of 9 parts, and some of the parts look like Swiss cheese. They are suffering from lack of fusion defect. What are the bad effect of that? You see, with the increase in void size, the mechanical property like ultimate tensile strength degrades significantly. So after some time, you can even not use that part anymore. You need to simply throw it, or you need to send the part for post-processing like hot isostatic pressing to be able to overcome it. Now, additive manufacturing itself is very expensive. If you need to do another step of post-processing like hot isostatic pressing, you are wasting time, you are burning a lot of money. No industry will like that. So you need to prevent it. How do you prevent? Going back to fundamental understanding. So this is the molten pool during additive manufacturing process. It looks like to me an watermelon. So if you look at the transverse section, I am talking about this plane where my cursor is, it will look like this. This is the transverse section of one particular track. You can also call it a fusion zone. Now during additive manufacturing, we have this type of track multiple times. So if you stack them together, it will look something similar to this. Lack of fusion originates from this unmelted white region. You see, this white region is not melted, and this is the gap between these consecutive tracks. How do you minimize this? One very easy approach would be to bring two consecutive molten pools to each other, and that distance will be called as hatch spacing. That means if you reduce the hatch spacing, you should reduce the lack of fusion void. Lower hatch spacing, low void, consistent with both experiment and calculation. Very easy. Now, beyond hatch spacing, there might be many other variables. How the molten pool look like, how the fluid flow is inside the molten pool, what is the temperature field, how heat is being transformed. Everything will impact on the formation of lack of fusion. Now, a simple hatch spacing adjustment may not be that effective always. So what we did, since we lack the fundamental understanding in all the directions, we take advantage of machine learning. So we know what are the variables that might be affecting the lack of fusion void. We came up with these 5. Hatch spacing, you have seen from the previous slide. Pool depth, pool dimension, also important. Marangoni number, if you do not know Marangoni number represents the strength of the fluid flow inside the molten pool. Peak temperature and Fourier number. Fourier number indicates the heat transfer rate. Now we have all these variables computed for 100 experimental cases for 4 materials, and then we came up with an index, lack of fusion index, purely driven by machine learning technique, and that gave us a formula of lack of fusion index as a function of all these 5 variables. And you will see that based on these, you can clearly delineate between the cases where you have voids with respect to the cases where you do not have that many voids. The small dots are gas porosities, but not lack of fusion defect. So this can give you an idea that how you can use the fundamental understanding. Where you do not have fundamental understanding, you take leverage of that and combine that with machine learning and come up with some quantitative index that can very easily delineate between cases where you are suspecting defects and cases where you do not have defects. What are the advantages? The advantages are, first of all, you can say that based on this index for a new set of processing condition, whether defect will form or not. If defect will form, then you simply do not use the process parameter. You will save the materials, you will save the time, you will save cost. And secondly, based on these, you can tell which material is most susceptible to lack of fusion defect under a certain condition. Second is gas porosity, our third porosity defect. Now, we need to understand how gas porosities form. Let's say you have a gas bubble. How this gas bubble formed? Let's say during the gas atomization process, there was gas entrapped inside the powder that suddenly popped up when you melt the material. This is the gas bubble. Now, if this gas bubble during the process comes out of the molten pool, then you are safe. You will not have any defect. So this time that it takes to come out of the molten pool is called time to rise, and this is defined by us for the first time. This time to rise depends on the pool dimension and also affected by the velocity of the gas bubble and Marangoni convection. That means the fluid flow inside the molten pool. The second time is time to solidify. What do I mean by that? If the gas bubble can come out of the molten pool before the molten pool solidifies, then you are safe. But if it does not come out before the molten pool solidifies, then that gas bubble will be trapped inside the molten pool and create gas porosity. So time to rise, time it takes to come out of the molten pool, versus time to solidify, the time the molten pool takes to solidify. So what we proposed, what about we have a dimensional number that is simply a ratio of these two numbers. If time to solidify is larger than time to rise, you are safe. We use the index, and once again we collected a wide variety of literature data for different materials, and once again we saw that very simple time index can tell you when gas porosities will form, when gas porosities will not form. And if gas porosities are forming, that same index can tell you what will be the volume percentage of that porosity. So density percentage is just 100 minus porosity percentage. You can see that with the increase in gas porosity index, the porosity is increasing, density is decreasing. We published this result last year. Sixth example is minimizing residual stresses and distortion. This is particularly important when you are printing a large part with many layers and hatches. Thermal stresses are accumulated, and that will significantly impact on the distortion. So this is a thermal phenomena, rather thermomechanical phenomena. So what we did, we started by doing the mechanistic modeling of additive manufacturing to calculate temperature. Then we take the temperature field to a commercial package, Abacus, for doing the thermomechanical calculation, where we get the residual stresses and distortion for a part. So you can see that that type of model can tell us or provides us the insight, scientific insight, that how a part distort depending on the temperature field. Like you see, we are depositing this particular layer and the laser beam is moving. This is the location 1, this is the distortion field. As the laser beam is moving from left to right, you can see the temperature field is changing, the distortion field is also changing. So that can correlate between the temperature field and the final distortion field. Moving one step further, you can use this information and get the spatial non-uniformity nature of residual stress. What do I mean by that? Now, residual stress, unlike distortion, is a vector. So you have different components. So I am taking two components, longitudinal, that means residual stress component along the length direction, and the transverse component, that means residual stress component along the width direction. Now you see, after the deposition of second layer, for both components, you see high tensile stress near the top of the deposited part. So you can see here, it goes from tensile to compressive. Negative stress is compressive, positive stress is tensile. So high tensile stress near the top of the component. Now when you deposit subsequent layers, that high stress will be partially alleviated. Why? Because you are reheating and recooling the part while depositing subsequent layers, and that reheating and recooling will alleviate that high tensile stress that was supposed to be here. Now similar high stress you can find near the top of 10th layer, and you will see that between two consecutive layers there might be sharp change in tensile stress, that are compressive stresses, and that may delineate two consecutive layers. That is a phenomenon very commonly encountered in additive manufacturing called delamination. Delamination means separation of two consecutive layers. It can also happen between the substrate and the part. The part can simply come out of the substrate because of high residual stress accumulation. So that is a separate field of study. Now what we can do is we can get some other insight if we take advantage of the modeling and combine that with machine learning. The most important advantage is understanding which variables are more dominating. You see, here we are talking about 5 complex variables. First is the temperature difference, that is the solidus temperature minus preheat temperature, stress developed per unit temperature change, beta delta E, volume, pool volume, substrate rigidity, and heat input. Now these are thermomechanical variables. What we did, we computed these variables using a mechanistic model that we just saw for different materials, and then we created a data set, synthesized that data set using machine learning, and came up with feature importance of those variables. You will see that controlling residual stress, this temperature difference is the most important variable. So if you want to control residual stress, you should focus on controlling this variable. And this is nothing new. If you see the common industrial practice in welding, you will see we often preheat the part to reduce the residual stress. So what you are doing, if you are doing preheating, that means you are reducing delta T for a particular material. So you are doing preheating to reduce delta T to be able to reduce residual stress. So see how machine learning can reveal some of the scientific understanding that we commonly practice in industry for many decades, even before people know of machine learning. So that's the advantage of these advanced computational tools. My 7th example is composition change. Now this composition change is very important for additive manufacturing, and you will see why. But before that, let me give you a context of what is composition change. Let's say you have a cup of coffee. Now I understand in Tampa, Florida, it's too hot to drink coffee, but in Iowa, we regularly drink coffee because of very cold atmosphere. So if you keep coffee, you will see the vapor, water vapor or water steam coming out just from the top surface of the coffee cup. When you talk about a weld pool or molten pool during additive manufacturing, same thing happens. Now, if you have a metallic alloy like stainless steel that has iron, that has chromium, nickel, manganese, those alloying elements vaporize from the molten pool. And when you finish the manufacturing process, because of the evaporation, the chemical composition of the part will be significantly different from the chemical composition of stainless steel 316 that you would expect. And when you have different chemical composition, that means your microstructure will be different, properties will be different. If you are talking about stainless steel, the corrosion resistance may be different. This is not a new field. People have done experiment and modeling in welding literature, and this is a work going back to almost 25 years from Professor Debroy's group. You will see during the laser welding of aluminum 5000 series aluminum alloy that is susceptible to lose magnesium, which is one of the preliminary alloying element apart from aluminum. You will see there is a depletion, magnesium depletion during the welding process. So how would you model that from the additive manufacturing context? And we just published this last year. So we have been talking about heat and fluid flow model to calculate the temperature. Once you know the temperature, you need to know, depending on that temperature, how different alloying elements will evaporate. So here the example is for a nickel alloy. We did the investigation for a nickel alloy, nickel-based superalloy. Now in that alloy there is nickel and there are all other type of elements. We also published a database a couple of years ago, vapor pressure with respect to temperature. Now when vapor pressure is equal to 1 atmosphere just above the molten pool top surface, that pressure corresponds to the boiling point of that material. So if you take 1 atmosphere and go here for aluminum, this is for aluminum, this is the boiling point. This database is very well known. We publish that database for wide variety of metals. Anyone can use that. Now once we know the vapor pressure, that means depending on the temperature field, we can get the vapor pressure of all these alloying elements. Now that vapor pressure is not the vapor pressure of the alloy because there are all other elements. What we need to know the thermodynamic activity of the individual elements inside that alloy. We can do that by using any CalFat package, GMAT Pro, Thermocalc, you name it, you will get this. So once you know this, you combine both of them and get the partial vapor pressure of chromium. Partial vapor pressure because chromium is not 100% in that alloy. There are many other things. So it depends on the mole fraction, partial vapor pressure. So once you know that, you will know the evaporative flux, the flux of evaporation of that particular element from the molten pool. And like that, you can calculate the evaporative flux for all alloying elements. When you do that, you will know how much composition will change because of the evaporation. Like this, for Inconel 939, which is a nickel-based superalloy, I am just taking the 6 primary alloying elements during laser powder bed fusion. You will see that elements like chromium and aluminum, they are very easy to evaporate. So their evaporative flux is quite high. But if you think of tungsten, which is very high, which has very high boiling point, practically does not want to evaporate. You see very little change, very little evaporative flux. So that means during the process, some alloying elements evaporate rapidly at a high amount and some alloying element just does not want to evaporate. So at the end, because of this selective evaporation, you will get a significant change in composition. And we did calculation for a wide variety of materials, nickel alloys, and you will see that some elements evaporate so significantly that their composition change is negative, like aluminum and chromium, for the example I showed in the last slide. To maintain the composition as 100%, the other less susceptible alloying elements, their composition increases. So you may say that, okay, everything is evaporating, how the composition is increasing? That is because some elements are highly susceptible, they are changing so much, their composition change is negative, but to account for that, to maintain that 100% weight, some elements need to be increasing in the form of weight percentage. And that is very much consistent with the EPMA results. We did experiments. This is with the collaboration with a university in UK. So they did all the experiments using EPMA, and they came up with the composition change during experiment. We did the calculation, and they are, at least the trend wise, they are very close. Last example, reducing surface roughness. Once again, surface roughness is important because it significantly affects the fatigue properties. So this is done in our department. If you think of a biomedical implant, they need to have very nice surface finish if you do manufacturing. Otherwise, if we put this type of implant in a body of a patient, they will feel difficulty in walking. This is an example of hip joint implant. This is another bone implant, titanium alloy, biocompatible titanium alloy bone implant made in UC Davis. You see that they have to do a significant amount of post-processing to be able to make this part fit for real use as bone implant. So additive manufacturing parts are susceptible to surface roughness. So how you can avoid that? You can print the part with tiny layer. So you will avoid the staircase effect and you will get very low surface roughness. But what will happen if you print a part with very tiny layer? We will take decades to print a part. So productivity will be significantly affected. So that's why this is probably not a good approach. What might be a better approach? Going back to basics and try to understand how surface roughness form in additive manufacturing. This is another work we published last year. So we identified that there might be 3 reasons in additive manufacturing because of which surface roughness happens. Geometric factor. Let's say the tracks that you are depositing have very high peak and then they are far apart. Then this peak and trough, they will create surface roughness. Instead, if you spread the liquid very nicely, that trough will be minimized and you will get a smoother surface. This is very elementary. Second thing is instability. If the molten pool is not stable like this, it is instable, it's forming ripples on the top surface, and there are 1,000 reasons of why molten pool can have ripple on the top surface, and we have shown some of the quantitative calculation in this paper. If you have those ripples, the track will also have ripples after solidification. So that is instability. Disintegration. If the molten pool cannot sustain its continuity and disintegrate and form island or ball during the process, that will also create surface roughness. So we came up with geometric factor, instability factor and disintegration factor, and combine these 3 factors to be able to understand how surface roughness happens. So what we did, we calculated those 3 factors, and then we have this surface profile measurement equipment where we can we use structured light scanning to be able to get the surface topography in 3D of printed surface. So if let's say this is the deposited surface, the top surface, you do scanning and you get the surface roughness profile. So now if you know this, you can take advantage of those 3 numbers, combine them into a surface quality number, and you will see that based on that you can understand the effect of variables like heat input, this is DED, powder mass flow rate, and come up with maps where high dimensionless surface quality number means rougher surface. So if you compare between 2 experiments B and C, C has higher surface quality number. You can see the surface is poor. So this is another example that if you go back to basic, understand why surface roughness happens, you can take advantage of that and understand the relative influence of important process variables that are consistent with the experiments. So, so far I have given 8 examples. Let me summarize what are the major contributions from our side in this field. So, first of all, control of grain structure and solidification morphologies using fundamental understanding of the process, combine that with grain growth model. So this is something we are very interested in, understanding the grain structure and microstructure and controlling that. Second is understanding the inhomogeneity in mechanical properties using modeling, machine learning and data analysis, because additive manufacturing is probably one of the very few advanced manufacturing techniques where we suffer from inhomogeneity in mechanical properties, and people have built their career on this. We want to provide some detailed insight on this area. Third thing is understanding the physics behind common defects like lack of fusion, surface roughness, cracking. Some of these things I have presented, but this is an ongoing thing because many things we do not understand, and there are thousands of materials, thousands of processing conditions. There are a lot to explore. Then improve scientific understanding to understand the evolution of structure, property and defect and their interrelation. That is the primary theme of my talk. So where we can go from here? One way is to combine all the tools that I have been talking about. I have been talking about different types of models, whether that can be a rigorous mechanistic model, a straightforward statistical model, or it can be a data-driven technique like machine learning. Sometimes I also have been talking about analyzing the data from literature or previously done experimental data. How we can put together and then build a framework that will virtually represent the physical printing system. So it's like a twin in the virtual environment, a twin of the physical hardware in the virtual environment. We call that as digital twin. So with Professor Debroy, I published this in 2019. That is the first concept of digital twin in additive manufacturing. After that, there have been many other digital twin papers on additive manufacturing. So essentially what it tells that you have a modeling area, you have a machine learning area, and you have a data analysis area that will communicate among each other, and also that will communicate with the physical system in terms of sensing and control. Still, so far, although we know the concept, although there have been many research in this field to be able to understand how to make a digital twin of additive manufacturing, but currently there is no digital twin of additive manufacturing that any one of us can use. There are building blocks, but not a complete digital twin after spending a lot of federal grants by different organizations. So this is an interesting path forward where all of us can contribute. Second thing, what I think we have a very good opportunity, particularly when we talk about applying the computational tools in additive, is quantum computing. Now additive manufacturing, now you can appreciate from my previous slides that these are computationally challenging process because your molten pool is very tiny, because often we talk about depositing layers that are thinner than human hair, and we are making real parts. Just imagine how many thousands of layers you need to deposit. How would you model deposition of thousands of layers? You need supercomputers. And when I say supercomputer, I am not talking about GPUs, I am talking about beyond that. I am talking about quantum computing. If you do not know what is quantum computer, so in regular computer, we talk about bits, 0 and 1. Quantum computer talks about qubit. So it depends on the quantum spin of the electrons and take advantage of that in the computing. IBM is one of the leaders, so this is a picture of IBM quantum computer. Now, if you have a .edu email ID, you can request 5 qubit of quantum computing capability directly from IBM without any cost. They provide this for educational purpose. You can create an account, run your Python code very easily. But this is limited to 5 quantum bit computing capability. Also, SBIR, which is supporting small business innovation research in this country, they have emphasized the need for quantum computing in 3D printing applications because of the enormous need in the computing in this area. So I think, to me, digital twin and quantum computing are the two most promising future direction when we talk about application of computational tool in metal additive manufacturing. So before I conclude, this is a recent book, once again with Professor Debroy, on additive manufacturing, theory and practice of additive manufacturing. So there have been many books on the engineering side, so we decided to talk about the theories because we are very, very interested in understanding the scientific principles or scientific theory of process structure and property relation in additive manufacturing. So we came up with this book published last year by Wiley, and to make this book student friendly, we have provided more than 100 worked out examples related to all these things that I was talking about, and how people can use some of the very easy, commonly available open source techniques to be able to do something for their applications, for metals, for polymer, for ceramics. So this is a book all of you can look at. Also, we put educational content on our YouTube channel. Our YouTube channel, or our group name, is Science and Technology of Advanced Material Processing, STAMP. We do manufacturing and material research. If you have a cell phone with you, you can scan this QR code. You will be redirected to the YouTube channel, where we try to put some educational content, some of our talks, some of our discussions, some of our new finding, like paper. Instead of going through a very lengthy paper, you can watch a 3-4 minute YouTube video on the paper and get a gist of it. So this is an educational channel. We are growing, but this will be something you may want to look at. And finally, all these things that I have been presenting today, these are not my work. These are the people who are at the background doing all this magic. So that's where I will conclude. And this QR code, if you scan, this will connect you with me, and this is my email ID. You can write me an email today, tomorrow, down the lane, anytime, with any questions. I'll be very happy to answer. So that's where I conclude.
This is great. This is great information for all of our students. So now the students, the floor is open for questions if you have any.